Hello everybody and welcome back to another AP1 review video. Today we're looking at conservation laws. Now if Newton's second law was probably the most important topic in this class, conservation laws definitely are in the runner-up for second, if not equal standing. So let's first look at the conservation of energy. And let's first review this idea of work. Energy is the ability of a system to do work, and likewise, work can be thought of as the change in a system's energy. So sort of understanding work before we plot on to the conservation of energy is a good thing to review. So work can be sort of defined as the change in a system's energy. You can change a system's energy by exerting a force on it. So our work can be thought of as a force acting on an object and moving it over some distance. So a force is applied, it displaces the object over some distance or displacement, and we can quantify the amount of energy that was changed by this idea of work. For being really pedantic here, we want to slap on a cosine theta, and this angle is literally the angle between the force and the direction the object is moving. In other words, you can't push a box up and expect it to go forward if that's your goal. So, in other words, here's our box on the ground. It's got a whole bunch of forces acting on it. It's got some kind of pushing force, tension from a cable maybe. We've got a normal force acting up on the object. Maybe we have friction acting back on the object, and maybe we definitely have the object's weight going down. If we're told that this box is moving across the ground, it has a displacement to the right, in other words, then only a certain number of these four forces we drew here is actually going to do work on the box. And the way we can figure that out is basically, if we think about this formula here, if F and X are arranged in a way such that this cosine theta is 0, then it's not going to do any work. So when is cosine 0? Cosine theta equals 0 when theta is 90 degrees. Oops, I spoiled myself here. Cosine theta is 0, not 90, when the angle is 90 degrees. So in other words, if F and X are perpendicular, that force does no work to make this displacement happen. So in this example here, our displacement's to the right. We have Fn pointing up. That's perpendicular to X. So in other words, this upward force is not helping the box move forward. Likewise, gravity is going directly downwards. That's still perpendicular to X, and pushing down the box is never going to help it go forward. So Fn and Fg are not going to do any work on the box. The work has to be done by some combination of the tension and the friction. So some things to note here. F of t is what's pushing the box forward. So in other words, there's a component of tension that is in the same direction as the x component here. That's going to be the adjacent component here, and that's why it ends up being the cosine here. So the angle between x and ft is just sort of the angle that ft makes with the horizontal here. So if we want to find the net work, we want to add the work done by tension plus the work done by friction. The way we do that is just kind of, we go through the crank here. We're going to replace the force here, F with the force. We're going to replace the displacement with how far it's moved, and we're going to look at the specific angle between that force and the displacement. So here we're going to have Ft delta x cosine theta, and then we do the same thing for friction. plus the force of friction times displacement. And then the cosine here, x is forward, friction's completely the other way. We get cosine of 180 degrees, which of course is -1. So we can replace that with minus f delta x. And we can go through and figure out what f actually is, mu Fn. You gotta do a little bit of work to figure out what Fn is going to be here, but that's a Newton's second law problem from here on out. So in other words, if we want to find the net work done on an object, we have to look at all the forces acting on that object and then figure out, just kind of plug them into the formula here for each force. You're going to write down an f delta x cosine theta for each force. If we really wanted to, we could write it down for gravity and the normal force, but because cosine of 90 is 0, that ends up canceling out anyway. Same with the normal force. So that's how we can find the net work acting on an object. So work is an object's change in energy. If you exert a force on it, I'm going to cause, I'm going to make that object move. I'm going to give it kinetic energy. The amount of kinetic energy you give it is equal to the work done. So this gives us sort of our work kinetic energy theorem. Which says that the net work done on an object is equal to the object's change in kinetic energy. So in other words, we're now able to connect an object's speeds with the forces acting on it. We can do this force analysis to figure out what the left-hand side is, work net, and then we can connect that to the initial and final velocities of the object. So that allows us to connect speeds and velocities to forces with work. Or we can just say, the change in kinetic energy, this much work was done on it. We could say this much work was done on it. How fast is it going now if it was going so fast in the beginning? So work kinetic energy theorem, the real conceptual idea here is the work done is the change in kinetic energy of that object. So everything we've talked about so far is external forces acting on one object. You only get work done when an external force acts. So work is done on a system by an external force. So for example, I jump in the air, I am the system, gravity brings me back down. Gravity, the earth, is an external force bringing me back down to the ground. So the earth did work on me to change my kinetic energy and bring me back down to the ground, speeding me up as I fell. However, we can redefine our system to include the earth. The earth's pretty cool. Let's let it play along. So we can define our system to include everything of importance. So now that I've included the earth in my system, we now have an earth person system. And if this kid is just, or person, me even, is just jumping from the ground, now there are no external forces involved. So there's no work being done, and all these forces are internal, which just means we're kind of swapping energy around. So if we have expanded our system to include everything important, so you might see words like the earth person system, now there are no external forces to do work. And in this situation where there are no external forces, we say that energy is conserved. So now in this new Earth person system, the Earth is not doing work on me to make me faster. What's happening is when I'm at the top of my jump, I'm above the ground, and I now have the potential to fall down due to Earth's gravity. So at this initial point, I have potential energy. Ug equals mgh. As I fall, it's not so much that the Earth is doing work on me to give me kinetic energy. It's that I'm now converting my converting my potential energy into that kinetic energy as I fall. And I can't get any more potential energy than kinetic energy than the amount of potential energy I started with. So if I have 100 joules of potential energy from this sweet jump that I did, I'm going to have 100 joules of kinetic energy when I hit the ground. Anywhere in between, I still have a little bit more to fall, so I have some amount of potential energy, but I'm moving faster than I was before at the top, so I have potential and kinetic energy in the middle, and that has to equal out 100 joules. So we're just switching the balance. At top, I have all 100 is potential, and I have no kinetic at the bottom at top. Now I've fallen somewhere in between. This stack's a little bit less. This stack is, maybe we're at a 60-40 balance here. But when I stack these two things on top of each other, not the scale, but you get the idea. It still has to equal 100, and then finally, so falling is in the middle. And then at the very bottom, all of my potential energy has been converted to kinetic energy, and that equals the 100 joules we started with. So at ground. Then I hit the ground. The ground, strangely enough, is not part of the Earth person system, and the ground is going to exert an external force to slow you down and change your kinetic energy to 0 at that point. So we really have to be careful when looking at work and energy of what we're defining in our system. So real quick, energy is conserved. That's an important thing. If we define our system right, energy is conserved within that system. If there are external forces, then energy is not conserved. Energy is conserved if no external forces are on the system. Which means that in our system, the energy at any point A must be equal to the total energy at some later point B. We just have to figure out of what energies are there. In our earlier system, we had potential energy at the top, and somewhere down the line, in between, the very top and the very bottom, we have some combination. We're at a different height, and we have some speed that we've accelerated to. At the very bottom, we can't fall any further, so there's no potential energy, and we're just at some final velocity at point C. All of these are equal to each other, so depending on what I wanted to know, I could set A equal to B, A equal to C, B equal to C, yada, 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 to figure out what I actually want to solve for. So you have this great power with conservation of energy, that the energy in any system with no external forces is equal everywhere. If I have a non-conservative force like friction, or air drag, let's use this example of the person falling. non-conservational force. I think the word form is conservative. Friction is a non-conservative force. It's going to look like it's taking energy out of the system, but really it's converting it into a different form, thermal energy, for example. So now if we include air drag, for example, I have some initial height. Maybe I've fallen all the way down to the bottom. I want to know how fast I'm going right before I hit the ground. So at point C, which is the ground. But now there's air drag, and there's some amount of work done by that air drag I'm going to subtract out. We can now, like if I know I'm going 5 meters per second at the ground level, and I fell from 10 meters, I could calculate how much work was taken away by drag compared to the case where there was no air drag. So just by subtracting out this non-conservative work, we can account for things like friction or air drag. So subtract away non-conservative work from initial state of system. So in other words, this is all the energy you start with, but some external force or non-conservative force, friction, drag, something else, is going to take away some of that energy you started with and convert it into a different form that doesn't make it to the kinetic energy in the end. And so we can make up this difference by subtracting it out. All right, that does it for energy. Just really think about the different kinds of energies we can have. We have gravitational potential. Just to summarize, we have kinetic, 1/2 mv squared, and we have spring potential energy, US 1/2 k, where this is the spring constant, and x squared, where x is the displacement of the spring. There's also gravity at a distance. If we're looking at planets and not just a person falling from a couple of feet, we have minus g m1 m2 over the distance between them. So note, this is going to look real similar to another formula on your equation sheet. You have g m1 m2 over r squared would be the force between two planets or suns or something like that. The energy only has one factor of r in the bottom. So really, if you're panicking during the AP exam and you're looking at your equation sheet, really make sure that you check the symbol on the left, whether you're looking for a force or a energy, and that will just think before, look before you leap. It's a common mistake people make. So one thing that is conserved is energy. Momentum is another thing that's conserved. So energy you want to use when basically you're changing speeds or you're changing heights. These things are built into the different kinds of energies, and there are no external forces, or at least no external forces that can't be treated in a simple way like friction can. We know how to do that. Momentum conservation, on the other hand, doesn't really concern itself with changing heights or displacements for a spring. Momentum conservation concerns itself with collisions. So if you have two things crashing into each other, chances are you probably want to use momentum to figure that out. Two things crashing is sort of a dead giveaway that you're going to use momentum conservation of some sort. Collisions imply use momentum. Because when two things crash, all they're doing is trading momentum around. Two cars crash into each other, M1 and M2. They have V1 and they have V2. After the crash, these things might be going different speeds. Maybe this one's still going forward, this one switched directions completely to go the other way. but these values all have to add up to the sum of the momentum we started with. So just like energy conservation said, energy at some point at the beginning is equal to some point in the middle is equal to some point at the end, momentum conservation says the total momentum you have before a collision is equal to the total momentum you have after the collision. So in other words, I have these two cars here. M1, V1 is going to the right. I have to include the momentum of that car. The second car is going the other way. Unlike energy, momentum is a vector, so I have to keep track of direction. This is just a simple one-dimensional collision, and so this one is just moving in the negative direction. Its negative velocity means it has a negative momentum. So momentum going to the right is positive, momentum going to the left is negative, and we've included both objects in our system for the before case. In the aftermath of the collision, I have M1 still going to the right, so its final velocity has changed, but it's still in the same direction, whereas this one is also going to the right. For this to happen, clearly V1 had to be either more massive or moving faster than the momentum of car 2, because in other words, this is a positive number. If both cars are going to the right after the collision, it's still going to be a positive number, and therefore that's how we know these are equal. So the total momentum we had before was originally to the right in the positive direction. Our aftermath case, where both cars are traveling to the right, means that that's definitely true as well. So we can, just from this setup of the equation, thinking it ends up positive, it had to start out totally positive, tells us that the first car had to have more momentum than the second car. So this is sort of this QQT thing. If I have an equation like this, how can I translate that to figure out information about our cars? In a more quantitative sense, if I were given actual numbers, I could solve maybe to figure out how fast car 2 is actually going. But the important thing is being able to set up the equation, including each object's momentum in each part of the collision, and then accounting for which way the objects are going for the vector direction. There's a couple kind of collisions you should be aware of that sort of help you build or put these equations together. What we have here is just a simple old inelastic collision. It's inelastic because, well, most real collisions are inelastic, and that means that momentum is conserved, but energy is not. When they crash into each other, you hear a big bang, the cars get mangled, they distort and twist from each other, and basically that happens because some of the kinetic energy the cars originally had is being transformed into thermal energy or sound energy or something else. So energy is not conserved in your ordinary inelastic collision. You can have a perfectly inelastic collision. Energy is still not conserved. But the key factor here is the objects stick together. So when we set up an equation with a perfectly inelastic collision, two objects, or maybe even three objects, stick together and they become one object in the end. One object can only move at one speed, and therefore what happens is we have, all our momentums to begin with. Maybe it starts out the same way as our previous car collision, but in the end, they're both going the same final speed, and they're both one object. All of their masses combine to give sort of the final momentum of the object. So essentially what we've written here is total mass of the one object we have left times the speed that it's going in the end. So this is essentially treating, objects, stick, and combine mass. So if you see the words perfectly inelastic collision, you need to set them up with one final velocity that they share in the end. Or if you can identify that it is a perfectly inelastic collision by looking for words stick together, move as one, so on, something like that. Something that suggests the objects are now one object. The last kind of, well, I guess there's two more for completeness sake. There's the elastic collision. Typically, because these are the ones where energy is conserved. So not only could you write an equation that shows the momentum before and after the collision, but you could also set the total kinetic energy before. So you could also have Ke before is equal to K after. And these are looking at the total energies before and after the collision. Because you have like 1/2 mv squared 1 plus 1/2 mv squared 2, the squared makes these harder to solve, and typically they're not great problems to solve on a test because they take a long time. There's a lot of tedious algebra to do, but conceptually you should know what an elastic collision is, and it does imply that the energy after the collision did not go into forms like thermal or heat or something like that. Typically, elastic collisions are really, really rare in nature. You can approximate elastic collisions with things like billiard balls. It's pretty good, but you still hear them click together. Really, you don't get elastic collisions until you get down to the atomic scale, where you're looking at, electrons scattering off other charged particles or gas molecules bouncing around in a container. But basically, energy is conserved. They're not as common as the inelastic type. The last one is an explosion. Not a literal fiery explosion, but basically it's a perfectly inelastic collision in reverse. One object breaks into multiple objects. But all of the pieces that are flying around after this thing explodes have to add up to the initial momentum you started with. So here's my one object traveling, minding its own business. Then it explodes into three pieces. M1, let's just say M. We have M1, V1 plus M2, V2 plus M3, V3. And typically, explosions are where you really get into sort of the second dimension. Remember that momentum is a vector, and so I need to sort of separate out what's happening in the x direction with what's happening in the y direction. So if I have a car that's really morbid, a car that explodes into three pieces and it's moving to the right, its initial momentum is mv, m1 vi, and it explodes into three pieces. M1v1x plus M2v2x, looking at only the x component of the velocity in each case. And you might need to do some trigonometry to expand those out, for example, as like v1 cosine theta or something like that. If it's moving to the right, its initial y momentum was 0, and maybe all three of these pieces have a y momentum. But conceptually, we can think that because it started out only going to the right, if it explodes off in multiple directions, these have to cancel out somehow. So there's no way that these could all be going to the right. At least one of them has to be going to the left or upward. Sorry, if left and right is x, then this is going to be, say, up and down, or kind of in the third dimension here, going in and out. In other words, these can't all go in the same direction, whatever direction that is. Because we started at 0, something has to cancel out so that we end up with 0 in the y direction. So conceptually, a system starting out only going in one direction, it explodes. All those pieces have to add up so that the total momentum is still only going in the x direction. So final momentum in the y direction or z direction or whatever has to be 0. All right, that is conservation laws, both energy and momentum taken care of. All you're doing is you're setting up what happens before. Take everything in your system that might be there and set it up to everything in your system at some later point. We'll do some practice with this later this week. Have a good one.